G'day everyone, welcome to Lecture 2 of Topic 1 of Unit 3, Heat and Temperature. This video will be covering the main ideas of Chapter 1.3 and 1.4 of Book 1. You should complete this reading before class. Here are the learning intentions and success criteria for this chapter. Please pause the video and attempt to complete the knowledge and skills table down here. Okay, so having a look here, we can see we've got a lot of cognitive verbs that relate to knowledge here. We've got define, explain, describe. So the first thing is, if we're going through this learning intention, we probably need to know, well, what is internal energy? We need to know how these two are, or how they're different. How are heat and temperature different? Because these are words we use very commonly in day-to-day parlance, but they do mean different things. And finally, what are these physical factors that connect heat and temperature? Alright, so in physics we refer to different forms of energy, kinetic, gravitational, electrical, heat, and in grade 8 we classified these as being potential energies, storages, or active energy, something being done. Now in senior years we examine them whether they're based off of macroscopic or microscopic energies. We're not really worrying about whether they're potential or not. A macroscopic energy is one that's exhibited by the whole object. Gravitational energy, how high something is; kinetic energy, how fast it's moving. These are two examples. The energy is a property of the whole system. Okay? However, as we've discussed in the previous video, an object at rest also has kinetic energy of the particles. The average of the movements is 0. My tablet here that you can see is not randomly sliding left or right across the table, but the atoms, the particles inside are vibrating, which means they have motion, they have kinetic energy. But this is microscopic kinetic energy. It's a property of the parts of the object or the system. Okay. Now, just to clarify what I mean by a system, my tablet could be considered a system. It has smaller parts inside of it, but it's a system. However, the whole tablet desk with my monitors and my keyboard, my mouse, this is also a system. None of the parts inside this system are also moving. The atoms are, but the objects aren't. We could consider a train with a person walking down it. The train itself might be still, but there's a part inside the system, a person walking down it, that is actually moving. So a system is just a way of thinking about a collection of things, and this collection could be a collection of atoms, or it could be a collection of objects. Other forms of microscopic energy could be the chemical potential energy between bonds in an atom, or nuclear potential energy that we discussed in Unit 1. Okay, but that's for the Year 12s. Alright. Microscopic energy, the syllabus will call internal energy, and we give it the symbol U. Now, this is just because it came between the letters T and V. It was either for time and velocity or temperature and velocity in the alphabet. They were looking for a connection, so they said, well, let's give the letter between it as the symbol for the connection. So they gave the letter U. Now for this unit, we're not going to consider chemical potential energy for heating or cooling objects. The chemists will, but we don't in physics. We're just going to deal with nice solid state objects like lumps of metal heating and cooling. And nuclear energy doesn't change at low temperatures, so we're not going to have to worry about that. And so our change in internal energy, and this is the big one, because we can really only measure the change in something, relates to the change in heat. And remember in the previous video we used delta Q, or Q as our symbol for heat, and delta Q for change in heat. So, for your first activity of this video, this is a Freya model. It's a good outline to help you practice with anything that asks you to describe or define a particular word in the syllabus. You can add an extra box for drawing a picture. Sometimes that's really good for biology, chemistry, and some of the stuff later in physics. But for this one we don't need to. I'd like you to write the word internal energy here in the middle. Okay, and then you're going to fill it out starting with the examples down the bottom. Okay, and the reason why is we're trying to work back to this, and then later when you do your study, you start here, you go, oh yeah, here's my definition, oh yeah, things I've got to remember, oh yeah, and here are my examples. This is you building up, and then this is for you recalling later on. So, start with some examples of internal energy, go back through the video if you need to, do some non-examples, write down any facts, looking in the text can be good for this as well, and then put a definition in your own words. If you want to copy a definition as well out of the textbook, that's good to do as well, but make sure you've got your definition as well. Your definition must come first. This is your study and consolidation and ability to synthesize bits together. Okay, pause the video, complete the table, and we'll pick up in a couple of minutes. Alright, welcome back. So, in grade 8, going back to grade 8, we discussed kinetic energy and how it relates to the movement of an object. And then in year 10, we learned how to calculate it using a formula. Kinetic energy equals half mass times velocity squared. But heat relates to the microscopic, the internal kinetic energy of the atoms themselves, and it's connected to the average temperature of the object. Right? So heat, microscopic kinetic energy, average temperature. There is a formula for this given in the textbook, looks like this, but it's not present in the formula book, the thing that your end of year exam will be based off at the time of recording. The text does have some questions on it, and it's really good practice for your algebra. They're not very hard questions, and there is a worked example I'll leave you to peruse. But what's good for this, and this is what's useful about formulas in physics, is that this describes how things are connected. So here I can see that, well, if I increase temperature, my kinetic energy will go up. Okay? Now this kinetic energy is talking about microscopic kinetic energy, but it's still kinetic energy. Okay, well if the temperature increases the kinetic energy of a particle, and the kinetic energy formula is this, if I know how big the particle is, I know how fast it's going. Or vice versa, if I know how fast it's going, I know how big it is. Or if I know how fast it's going and how big it is, I can work out how hot the things are. All these things, these rules allow you to talk about connections, and that's a really good skill to have, because you get given all these formulas on your formula sheet. You get given the answers basically there in your formula book. You just got to read them. So, have a go with those questions. Or don't, I guess it's up to you really, but it's good practice and it'll help you consolidate and connect the ideas. Last bit is I want to talk about making a cup of tea, a cup of coffee. Now, when we go to make a cup of tea, we boil water. I want you to pause the video, I want you to write down as many things that could influence how hot that water would be after a given time. Hopefully there are two major ones you should be able to come up with. Okay, so hopefully you picked up the first one, that if there are more mass of the water, the lower the temperature after a period of time. Or if you're thinking about keeping the temperature constant, it takes a lot longer to boil a lot of water than boil a little bit of water. And you actually do a lab with this in year 9 where you're heating up two different volumes of water and comparing the gradient and stuff, the slope. So the first bit is that more mass, the smaller the temperature change. If I heat up 2 jugs of water for 5 minutes, one has 100 mils and one has 300 mils, the 300 mil is not going to be as hot as the 100 mil. But we can write that as a formula. We say that mass is proportional to the inverse of temperature, or the change in temperature, or that the change of temperature is inverse to the mass, or proportional to the inverse of the mass. Okay? This is a really important thing to think about when you're doing your student experiment, in how you communicate relationships that you find. Now the other though is the power of the jug, and that might not have been as easy, or how much thermal energy we're giving the water. If we give you more energy, it gets hotter. If we give you less energy, it's not as hot. We say that they are proportional. Okay? More energy, larger temperature change. Q is proportional to change in T. We give more Q, we get a bigger change in T. we can put these together as well. Now, these proportionalities, you can't actually calculate anything with proportionalities, so we need to create a constant. So if we combine these, so see I've got delta t here, delta t here, delta t here, but here I've got 1 over m, and here I've got q on the top, so it's q over m. But we need to slap a c in here, we need to slap a constant of proportionality in there. This is called specific heat capacity. I'm not going to write that down because it's going to be a part of our later videos. And this value of c gets used a lot. It won't always be specific heat capacity. We will look at this property with our next lab, and it'll be a fairly big focus. Okay. What I want you to take from this idea is that if we're going to heat something up, we need to think about how big it is, and we need to think about how much energy we're giving it, and that's it. Okay. We have a formula, and we'll practice using that formula in a little bit. Alright, so in this video, we've defined internal energy and how it's changed. We've connected thermal energy to temperature, and we have clarified that they are different. And we've discussed the physical factors that go into thermal energy and hence the change of temperature. For your entrance lip to class, I'd like you to complete questions 1 to 4 in chapter 1.3 and questions 1 to 5 in chapter 1.4. Check your learning PDFs. You can copy your answers to that into the 3.1.2 space on eLearn. Thanks very much for listening. Have a great day.